Okay, so class 31, we're going to talk about complex zeros and the fundamental theorem of algebra. So our goal at the end of this class is to be able to take any polynomial and write it in completely factored form. X minus a 0, x minus another 0, x minus another 0. And this is what we were doing last class. We were able to do this, except that the examples that I chose last class, I chose very carefully. So, so that we would be able to do it. So today, we're going to look at some broader examples and see how we can still write this in completely factored form. So let's say I want to take p of x equals x squared plus 1, and I want to write it in completely factored form. Well, the factor theorem says that if I solve x squared plus 1 equals 0, I'll get zeros for the function. And then I can write x squared plus 1 as x minus, just plop my two zeros in there, and I'll have written it in completely factored form. So finding the zeros comes from solving where does the function equal 0. So I'm trying to solve this. I get x squared equals -1. Then what should I do? Square root both sides. And I get x equals plus or minus the square root of -1. Now, up until this very moment in your math education, we have told you there are no solutions, right? There are no real solutions because we lived in this world of real numbers. You can't take the square root of a negative number. You can't come up with a number that when you multiply it times itself, you get a negative, right? Because you say, okay, well, can't be 1 because 1 times 1 is +1. Can't be -1 because -1 times -1 is also +1. So there is no real number that you can square and get -1. So we have no number yet that you can square and get -1, but we said, I'd really, really like there to be one. Because if there was one, I could put it right here, and I would be able to factor this polynomial. So we invent it. We're going to call the square root of -1 the letter I. We're just going to say, pretend there is some number that when you square it, you get -1, and let's name it I. So it sounds a little crazy to just pull something out of thin air, to just invent it because we want it to exist. But that's what our entire numeration system is. It's an invention based on necessity. So think about the way you learned math growing up, going through elementary school and middle school and high school. The first thing you learn is how to count. And you go 1, 2, 3, 4, and you can count like 1 to 10, right? And then you learn that there are numbers after 10, right? And you can count further and further. And then the next revelation in your mathematical world is that there's a special number called 0 that means nothing, right? So because you don't, when you teach a child to count, you don't have them start at 0. It's 1 thing, 2 things. So 0 is like an invention. It's a brand new, and it was actually a revelation in the history of math, was the invention of 0 to represent nothing. So that's your first invention. And then we have negative numbers, which we just invented to represent something that we wanted to be able to represent with numbers. And then we decided, somebody told you, actually, those aren't the only numbers. There are also numbers between the numbers, right? The fractions and decimals. And then there's the invention or discovery of irrational numbers, numbers that can't be written as a fraction. So it's not that crazy when you look at it in the whole context of the history of the development of numbers that we would invent something because we want it to exist. So once we have this number, I, which when you square it, you get -1, we can just plop it in here. X minus I and X minus -I, and we've got this thing in completely factored form. let's just double check that when we FOIL this out, we do get x squared plus 1. So when I FOIL, first I get x squared, then I get plus ix minus ix, and then I get minus I squared. So my ix's, my outer and my inner ix's, those cancel. Then I have x squared minus I squared. But what does I squared equal? Negative 1. Yeah, because we said I is going to be the number that when you square it gives you negative 1. That's how we invented it. I is the number that when you square it you get negative 1. So this says, whoops, that was a minus. So this says x squared minus, and then replace the I squared with a negative 1, and you get x squared plus 1. So you do get the original function back when you multiply out the two factors. So this is our new definition. I is going to be the symbol we use to denote the square root of negative 1. So if I want to take the square root of any negative number, I let I take the place of the square root of negative 1. So if I want to take the square root of negative k, I can rewrite that as the square root of negative 1 times k, which I can break into two square roots, the square root of negative 1 and the square root of k, and then replace the square root of negative 1 with an I square roots of k. So if I want the square root of negative 49, I can write this as the square root of negative 1 times positive 49. Break it into two square roots, the square root of negative 1 times the square root of 49. What's the square root of negative 1? I, and the square root of 49 is 7, so we get 7I. Square root of negative 8. This will be the square root of negative 1 times positive 8, which is the square root of negative 1 times the square root of 8. Square root of negative 1 is I. So I could write this as I square roots of 8. Or I could simplify the square root 8 to be 2 root 2. 2I root 2. Either of these would be acceptable. And then I squared, well, I is the square root of negative 1. I want to square it. And when you square a square root, they cancel, so you get negative 1. Make sense so far? Okay. So we have this new definition I. The purpose, we invented it to be able to factor polynomials that aren't completely factorable. But so now we're just going to do a little bit of work. Now that we've invented this thing, we have to like get a feel for it. How does the arithmetic with this new number work? So the letter I stands for imaginary. And we say a complex number is a number that looks like a plus bi, where a and b are real numbers. Okay, so it's a sum of a real number plus an imaginary number. A real part and an imaginary part. So for example, 2 plus 5i is a complex number. 2 is the real part, 5 is the imaginary part. 3 minus 4i. 5 plus 0i is a complex number, even though that's just the number 5. Okay, so we still consider that a complex number. So regular old real numbers, all the numbers that we've been using for most of our lives, those are a subset of the complex numbers. And the strictly imaginary numbers, like -7i, or 8i, or 5i, those are also complex numbers, a subset of the complex numbers, because you can write them as 0 plus bi, whatever they are. So the way this looks is we've got real numbers, you know, your standard numbers that we've known that are our good friends. And then over here we've got imaginary numbers that we just invented. And the overlap, this whole thing is complex numbers. So real numbers look like 5 or 8, -6, right? 2/3, regular old real numbers. And then we have strictly imaginary numbers, which are like 3i, I, -2i, numbers with i's in them. And then the overlap, sorry, there is no overlap. This is empty. But then there are complex numbers, which are like 2 plus 3i. Has a real part and an imaginary part. It would be in the real circle, which is within the complex circle. So the number 3 is a complex number because you can write it as 3 plus 0i. Now, an imaginary number is a number of the form a plus bi, where a is 0 and b is not. So that's what you call a strictly imaginary number, a number like 3i. Right? It's just got a real part of 0. I think that yours has everything written correctly. I have a little typo in mine. So we want to be able to do arithmetic with these new kinds of numbers, these new complex numbers. You can add, subtract, multiply, and divide them, same way you would do with radical expressions. Just remember that I squared is -1. So I'm going to just skip this first one. If I want to add 2 plus 3i plus 1 plus 5i, if you treat the I like a variable, you just combine like terms. So this would be, you add the 2 and the 1, add the real parts, and you get 3. Then add the 3i and the 5i, and you get 8i. Just combine like terms. Add the real parts, add the imaginary parts. Subtraction works much the same way. All you have to do is remember to distribute that negative sign. So this says 2 plus 3i minus 1 minus 5i, and combine like terms. 2 minus 1 is 1, 3i minus 5i is -2i. So addition and subtraction, nothing special here. Just treat the I like a variable. Multiplication, same thing. FOIL. Just FOIL as though that I were like an X. So we have 2 times 1 is 2. That's my first. Outer is 2 times 5i, which is 10i. Inner is 3i times 1, which is 3i. And last is 3i times 5i, which is 15i squared. So I work on combining like terms here. 10i and 3i is 13i. And I squared is really -1. So this is 15 times -1. So this is 2 minus 15. So I have negative 13 plus 13i. All right, take a couple minutes in your groups to do part E. All right, so I'm going to FOIL 2 plus 3i times 2 minus 3i. We do first. 2 times 2 is 4. Then the outer, 2 times negative 3i is negative 6i. And then the inner, 3i times 2 is plus 6i. And then the last, which is negative 9i squared. So my minus 6i and my plus 6i cancel. So I have 4 minus 9i squared. But I squared is really negative 1. So this is 4 minus 9 times negative 1, which is 4 plus 9. 4 minus negative 9, which is 13. So something magical just happened. I took two complex numbers, both that had imaginary parts, and I multiplied them together, and I got my good old friend 13, regular old real number. So we kind of like that. We like to be able to manipulate things sometimes to get rid of imaginary numbers. So it's helpful to be able to do that. So what made this happen is that my two numbers, 2 plus 3i and 2 minus 3i, have a special relationship, and they're called complex conjugates. So the conjugate of a number a plus bi is a minus bi, and vice versa. The conjugate of a minus bi is a plus bi. So for example, the conjugate of 2 plus 3i is 2 minus 3i. And when you multiply two conjugates together, you get a real number, no imaginary part. So this is going to be so handy that it might be helpful to have a shortcut for how to multiply two complex numbers, complex conjugates together. So a plus bi times a minus bi. We FOIL it out. First, a times a is a squared. Outer is minus abi. Inner is plus abi. And last is negative b squared I squared. The ABI's cancel, and I get a squared minus b squared I squared. But I squared is really negative 1, so this is a squared minus b squared times negative 1, which is a squared plus b squared. So an example of using the shortcut, 2 plus 3i times 2 minus 3i. A is 2, b is 3. So a squared plus b squared is 4 plus 9, which is 13, which is what we got, but when we FOILed it all out. It's not important to memorize the shortcut. You can always FOIL it out if you forget, but it's just handy to have. The first thing that it's going to be really useful for is dividing complex numbers, doing division. So we've already done addition, subtraction, and multiplication. Now we're going to divide complex numbers, and this is going to be a handy little trick to have. So if I want to divide 2 plus 5i over 2 plus I, I want to make this look like a plus bi. I want to come up with an answer that's in the standard form of a complex number. So having i's in the denominator is a problem, right? Because I can't make it look like that as long as I have i's in the denominator. So I'm going to use my handy trick of one way I can get rid of i's is to multiply by the conjugate. And because this is a fraction, you can always multiply by 1. So I'm going to multiply by 2 minus I over 2 minus I. 2 minus I because it's the conjugate of the denominator. And I know that when I multiply conjugates together, I'm going to get a real number. All the i's will go away. So in my numerator, FOIL those two complex numbers. And we get first is 2 times 2, which is 4. Outer is negative 2i, plus the inner 10i is 8i. And then I have minus 5i squared. 2 plus I times 2 minus I should be 2 squared plus 1 squared, which is 5. FOIL those together, you should come out with 5. And then just finish simplifying this numerator here. I squared is really negative 1. So this minus 5i squared really says plus 5. So I've got 4 plus 5 is 9 plus 8i over 5. And then my last little trick so that I can make it look just like this, standard form of a complex number, is to divide the 5 into both pieces of my fraction. So I'm going to have 9/5 plus 8/5 I. So what do you think? Not too crazy, right? Here's another nice little thing. Your graphing calculator has an I button, the second function over the decimal point. So I can type in 2 plus 5i divided by 2 plus I, and it gives me 1.8 plus 1.6i. Is that what I got? Is that equivalent to my answer? I could hit math, enter, enter to get as a fraction. 9/5 plus 8/5 I. You can't, which is, it's very sad for me. I really want to be able to do that, but you can't. But it will do arithmetic with i's. Okay, so that brings us, now that we've invented a new number and learned how to work with it, that brings us to the fundamental theorem of algebra. We can take any polynomial of degree n and factor it into n linear factors. So if it's degree n, it's going to have n linear factors and n zeros. Some of those zeros might have imaginary parts. Some of them you might have to count according to their multiplicity, like if x equals 2 is a 0 twice, you count it as 2 zeros. So you're going to have some real with no imaginary part, right? Some complex with an imaginary part, and some you might have to count according to their multiplicity. So this is the fundamental theorem of algebra. It's a big deal, something called the fundamental theorem, right? That you can take any polynomial. If it has degree n, that means you can write it into n linear factors and with having n complex zeros. Some real, some non-real, counting the multiplicities. So this is actually analogous to another really famous theorem that you learned in, like, I don't know, sometime in elementary school, maybe middle school, called the fundamental theorem of arithmetic, which, anybody remember doing something like this? And then you can write the prime factorization of any number. So in this case, it would come out as 2, 1, 2, 3, 2 to the 5th. So the fundamental theorem of arithmetic says that every real number has a unique prime factorization. So the fundamental theorem of algebra is analogous, except now instead of factoring numbers, we're factoring polynomials. Degree n, you can factor it to n linear factors. So for example, here's a polynomial, x minus 2 cubed times x plus 2 squared times x plus 5 to the 4th. How do I know it's a 9th degree polynomial? Yeah, add the exponents. So if the highest exponent here would be an x cubed, and the highest exponent here, if I multiplied it out, would be x squared, and here would be x to the 4th. And when you multiply those, you add the exponents, so you get 3, 5, 9. So if you were to multiply that all out, which would take forever to actually do all that multiplication, not forever, but a long time, it would be tedious. So it would be tedious to do all that multiplication, but you can imagine if I were to do all that multiplication, all my leading terms would multiply together, and I would get an x to the 9th as the highest exponent. So this guy has 3 distinct zeros. It has a 0 at x equals 2 with multiplicity 3, because that's a factor 3 times. It has a 0 at negative 2 with multiplicity 2, because x plus 2 is a factor twice. And it has a 0 at negative 5 that has multiplicity 4, because x plus 5 was a 0 4 times. I mean, it was a factor 4 times. So if you were to write this all out without using exponents, we would have 9 linear factors. And we have 9 zeros. Only 3 of them are distinct, but there are 9 zeros because we count the multiplicities. All right, so here's a cubic, x cubed minus 4x squared plus 5x. How many zeros does it have? 3. Fundamental theorem of algebra says that if you have a polynomial of degree n, there are n factors and n zeros. So when I go to this problem, we see x cubed minus 4x squared plus 5x. What's the degree? The degree of this polynomial? 3. The highest power on x is a 3. Oh, I see where you're getting 6. You were adding the exponents. That only works if everything's multiplied. Yeah. This is already all multiplied out. So if it's written in factored form, like this one, we can add those exponents because these are all multiplied together, not added. So here, my degree is 3, which means there are 3 zeros, 3 factors. Okay, so let's find them. So if I want to find factors or zeros, start by writing down the function plus 5x. Well, I can get one factor because there's a factor that goes into all 3 terms. What would that be? X. So I could write this as x, factor that out, times x squared minus 4x plus 5. And does x squared minus 4x plus 5 factor? Yeah, minus 5 minus, I don't think it does factor. minus 5 plus 1, but that would give you a minus 5 as your last term. I don't think it factors. So this I should say doesn't factor easily, right? We can't just look at it and get the factors like we often can. And up until today, we would have just said it doesn't factor, right? But I do know that I should be able to write that because it's a quadratic, it has degree 2. I should be able to write it as a product of two linear factors. X minus. And then these things that are missing are the zeros of x squared minus 4x plus 5. So let's find those. X squared minus 4x plus 5 equals 0. Use the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And I get x equals 4 plus or minus 16 minus 8 is 8. 4 plus or minus root 8 over 2. Yes. Don't know why I wrote that. Thank you. That makes a difference. So now I have 16 minus 20, right, which is negative 4. And what's the square root of negative 4? 2i. So we have 4 plus or minus 2i over 2. Divide the 2 into both pieces, and you get 2 plus or minus I. Are my other two zeros, which once I have them, I can get my other two factors. 2 plus I and 2 minus I. So plop them in up here. 2 plus I, 2 minus I. Make sure you put parentheses when you're doing that because you want to do x minus that whole 0. So you have to put extra parentheses in there. So my zeros are going to be, so these are my factors. My zeros, I know are 2 plus or minus I. And the one that goes with x would be what? 0. So when you're finding the zeros of a function, once it's all written out in factored form, the way you find the zeros is you take each individual factor, set it equal to 0, and solve it. So this factor of x, when I set it equal to 0 and solve, I don't even have to do anything, right? You just get x equals 0 as one of your zeros. And then set each of these factors to 0, and you get 2 plus or minus I as your solutions. All right, so keep in mind, you might have noticed in this example, the two complex zeros were conjugates of each other, 2 plus I and 2 minus I. Not a coincidence. That will always happen because the way you end up getting complex zeros is from the quadratic formula, and the thing under the square root comes out negative. So you're always going to have something plus or minus something I. Right? So you're always going to have complex conjugates appearing together. So for example, x squared plus 4, I want to find its two zeros. It's a second degree, so it should have 2 zeros. I find them by setting x squared plus 4 equal to 0. So I get x squared is -4, which means that x is plus or minus the square root of -4, which is 2i. 0 plus 2i, 0 minus 2i. So those two are complex conjugates. And that means I can factor x squared plus 4, x minus 2i, x plus 2i. So just keep that in mind. You always get complex zeros in conjugate pairs. They always come in conjugate pairs. You can't have just one complex zero. All right, so before we do this last bit, I want to look at, actually, I'll just make one up. I want to find an equation for a fourth degree polynomial that has zeros at 5 and 3i. So it's a fourth degree polynomial, right? Which means how many zeros does it have? 4. I only gave you 2. So one of them you can say immediately has to be another 0. Which one? We should be able to come up with a third 0 very quickly. Yeah, -3i. So complex zeros always come in conjugates, so you must have -3i as a 0 also. Okay. And if those are the only zeros I give you, is it possible that my fourth 0, because now I have 3, 5, 3i, and -3i, is it possible that my fourth 0 is complex, and has an imaginary part? No, why not? Because there would have to be a pair that goes with it. Yeah, so it couldn't be a fifth degree polynomial. Right, very good. Yeah, so you can't have another complex because then I would have 3 complex zeros, and you can't. They have to come in pairs. All right, so my fourth 0. What is my fourth 0? If I've told you all the zeros here, I gave you all the real zeros. What has to be true about the 5? It's got to have a multiplicity of 2. So it's a 0 twice. Well, I'm saying, assuming I told you about all the zeros. But there isn't like a 0 at x equals 3 that I just didn't tell you about, right? Assuming I gave you all the real zeros. If it's a fourth degree polynomial, I have to be able to write it as a product of 4 factors, right? And I have 3i, -3i, and 5. X minus 3i, x plus 3i, x minus 5. If there are no other zeros, x minus 5 has to be repeated because there's a missing factor. It has to be that x minus 5 is a 0 twice. Assuming I gave you them all, right? Not holding out on you. And you can put any constant in front of here, and you'll have all the same zeros. Because complex zeros always come in conjugate pairs. So if 3i is a 0, then negative 3i is a 0. If 2 plus 5i is a 0, then you know 2 minus 5i is a 0. They always come that way. Yes. Yeah. Because the imaginary part, they always come from using the quadratic formula or solving a quadratic. So I end up with this plus or minus that happens from the quadratic formula. And they always come out in conjugate pairs. Yeah. So if I have a polynomial written all out in factored form, the way you find the zeros of a polynomial is you set the polynomial equal to 0, right? And then once you have it all in factored form, set it equal to 0, you set each factor to 0. Yeah. So then if I came out with x equals 5 as the answer to setting this equal to 0, the thing in this parentheses had to be x minus 5. So if I give you the 0, you can go backwards to find the factor. If I give you the factor, you set it equal to 0, and you find the 0. Okay, so this very last little bit of the lecture says that if a radicand, that's just a fancy name for the thing under the radical, thing under the square root. If the radicand is negative, you rewrite everything in terms of I before doing any operations. So in real numbers, we're allowed to do operations in and out of the square root. So let's say if I wanted to do, shorthand for real is double line through a capital R. So if I wanted to do square root 20 times square root 5, in real numbers, I could just multiply what's under the square roots. This is the same thing as square root 20 times 5, which is the square root of 100, which is 10. Now, if I were to do that with imaginary numbers, if I were to try to follow the same rule, I have negative square root 20 times square root of negative 5. It seems like these are two very different questions, right? Two very different pieces of arithmetic. To take the square root of 20 times the square root of 5 versus the square root of negative 20 times the square root of negative 5. Seems like you would get a different answer. But if I were to follow this same rule, negative 20 times negative 5, I would get square root of positive 100, which is 10. But these are very different questions, right? So we can't actually do this. This is not allowed with imaginary arithmetic. So this is kind of the only big difference in terms of arithmetic with imaginary numbers. The correct way is to change everything to i's before you do the arithmetic with the square roots. So I have square root negative 20 times square root negative 5. rewrite this as I square roots of 20 times I square roots of 5. Take out the square root of -1 from each of them first. And then we have I times I is I squared times, and now we can follow the rule where you're allowed to multiply what's under the square roots. 20 times 5 is 100. Square root of 100 is 10, and I squared is -1. So you come out with -10. Which just feels better to have a different answer from when using than the real analogous problem. Mm-hmm. Yeah, right. Yes.
So I squared is -1.
I is just I, and it represents the square root of -1. It's just a symbol that we use to represent the square root of -1. All right. Ooh, good question. I cubed. I'm going to use some rules of exponents to help me figure this out. I cubed I could rewrite as I squared times I, because I squared times I to the first, you have like bases, you would add the exponents. So I just broke it down to I squared times I, and I squared is -1. -1 times I is -I. So I cubed is -I. Let's see, what's I to the 4th? 1, yeah. Because you could think of the I squared, I to the 4th, as I squared times I squared. There's other ways to think about this also. And so this is -1 times -1, which is 1. And then I to the 5th, well, that would be I to the 4th times I. And I to the 4th we now know is 1. So this is I. And you get this pattern, this repeating pattern. I, -1, -I, 1. I to the 6th would be -1. I to the 7th would be -I to the 8th would be 1. Just keeps repeating. Let's say I wanted to do I to the 25th. What number less than 25 is a multiple of 4 and the closest to 25 you can get? 24. So I could rewrite this as I to the 24th times I. And I to the 24th, that would be I to the 4th to the 6th. And what's I to the 4th? 1. And 1 to the 6th is 1. So this is 1 times I, which is I. So you can figure out I to any power knowing that I to the 4th is 1. And knowing the first 4 exponents. I think there actually is a homework question similar to this one. So good question. All right, so we've got 10 to 15 minutes to work on the activity polynomials with complex zeros. So I just gave you several polynomials. I want you to write them in completely factored form. Okay, and each one comes with a little hint of the best way to proceed. Yes.